All right, let's go ahead and get started. I wanted to take a little bit of time and talk about this. Let me dim the lights a little bit. Let me zoom in a little bit. So first off, a little bit of housekeeping. I graded your homework number 1, and I posted the grades on MU Online. And what I did was I tried to go through your spreadsheets and see if I could identify any mistakes, and if so, try and reference them. If you go on to MU Online or onto Blackboard, whatever you want to call it, you should be able to go to your assignment and view comments, that I left. I think I checked to make sure that works, so that should work pretty well. I wanted to go through a couple things, however, just so that everybody's clear on some stuff. So I have here a PDF of the solution based on this input. Now this input is directly the stuff that came from example 1. So my first, I guess, piece of advice would be, try and go through your spreadsheets to ensure that you're at least achieving the same results as what's on this solution. It's not for a grade or anything, but here very soon you're going to need some of this data to be able to do some of the homework. And it is what it is. For instance, when we compute live load distribution factors, in order to do that, you need a moment of inertia. And if this isn't computing the correct moment of inertia, you're not going to get the right distribution factor. So, and then nothing I can do about that. That's just the way the spec's written. So you're going to want to make sure that this spreadsheet is generating the appropriate output. Now, one thing I'll point out, just a couple things. I'd argue that if there was one mistake across the board, it probably had to do with just labeling and bookkeeping. For instance, one mistake that popped up quite a bit was I would find spreadsheets that only had one effective flange width, and they would say it's 120 inches or what have you, but then the spreadsheet would then report different section properties for interior and exterior girders. And the difference between an interior and an exterior girder is that the effective flange width is different. So there's no way that you're going to get the same answer as you did. So you'll want to make sure that your spreadsheet can incorporate that. The second thing also is, again, labeling. There was a lot of instances where the data followed, and then we had to do another section, so we'll just throw another little cell here off to the side and put another effective flange width. And that's fine, but later on, when you've really got to go back and reference some of these values where you need section moduli for the bottom flange on all these different sections, if it's not well labeled and well organized, then it'll create problems down the line. So I've provided this. It's a complete positive and negative bending region solution. So if I zoom it out, here's the positive and there's the negative. You can see the other two sections down below. It's probably not a bad idea, so here's the solution in Excel. It's probably not a bad idea to maybe do something like this. This is just something that I did to go through and check your sheets. Like what I would do is I would change your input, and then I would print this out. And if this wasn't matching, then I'd figure out, okay, what's going wrong? Okay, and that's sort of how I approach grading. Most of the mistakes, if we actually went into the calculations, were really just, they were minor in nature. I put a multiplication sign instead of a subtraction sign, or I'm referencing the wrong cell and I need to drag this down. It's not that big of a deal, but there's really dollar for dollar, some of the most valuable time you're going to spend is ensuring that this data is correct for future assignments. Okay? Sound good? You have a question? No, I'm not giving you that. I want you to build it on your own, because it's got to be built in a fashion that you're comfortable with. Now, this one's the one I got to draw the line somewhere. I want you to go through the process of doing this. No, the PDF, I can PDF that if you want. Sure. Yeah, that's fine. I'll PDF that and attach it. I have no problem with that. No problem at all. Okay, a couple things. I forgot that I hadn't posted the solution to the senior design page. I'm more than happy to do that. I'm more than happy to do. No, yeah, no problem at all. No problem. Yeah, I just haven't had time because I can't link the classes because the grading's different, so I literally have to post it twice. And I'll be honest, sometimes I forget. But no, absolutely. All right. I posted all the lecture notes and all the homework assignments. Did you all see that? So all that's there. Okay. Any other questions? Okay. I didn't get a chance to check, but I think just about everybody got homework 2A done, right? That was a pretty short assignment, wasn't it? Wasn't too bad. Next one isn't so short. But, caveat, I'm giving you 2 weeks on it. It's not so bad in that regard. So, but we got a little bit of, stuff to talk about before we even, delve into assignment number 2, or that next assignment. The next assignment is primarily going to be on live loads. So, we got some stuff to talk about there. So, before I continue, any other questions? Okay. All right. Let me minimize this, and let me bring up this real quick. Okay. So I'm not going to belabor this presentation at all because we've already been through this. But I want to go back to some of the material that we discussed last time, which is in particular related to bridge loading. Now, there really wasn't a whole lot to say on permanent loads. It's just the self-weight, pretty basic stuff, really. I mean, take the unit weight of a material, multiply it by the area to get a weight per foot, stuff like that. And a lot of the load computations that we did for dead loads fall mainly on a lot of common sense, just pretty basic ideas. As long as you're keeping track of units and you're just assuming all the load gets equally distributed to each girder, it's not tough. It's pretty straightforward stuff. So there really wasn't much discussion about the dead loads other than they're there and we need to compute them. Live loads, however, are a little more complicated. Okay? We spent a fair amount of time last time just defining what the heck the live loads even were. Okay? Because as we said last time, we're not designing bridges for Honda Civics. Okay? We have a particular type of vehicle that we're designing for, specifically exclusion vehicles, things like concrete mixers, tractor trailers, truck traffic. Heavy vehicular truck traffic is what we're designing for. And AASHTO represents vehicular loadings in the United States with the HL93 live load model. We used to use the HS2044, which was a spec developed back in the 1940s, specifically 1944. Fast forward a few decades and you find that the HS20 just isn't predicting live load the way that it should. The red line is, a moment ratio. In other words, what load are we using versus what load we're actually getting. And you can see before the HL93, the loads were way higher. Now they're pretty well even. And the same story with shear. I'm going to real quickly summarize the stuff we talked about last time. So the 3 components of the HL93 are the two vehicles, the truck and the tandem, and a lane load of 640 pounds per foot. So here's the truck, front axle of 8 kips, 2 rear axles of 32. Front axle spacing is a constant 14 feet. Rear axles vary between 14 and 30. And in most cases, what's that rear axle spacing going to be? 14. You're going to lump those loads as close together as you can to maximize the force effect. Tandem, 2 25 kip axles, 4 feet apart. And then we did a lot of discussion about the combination of those loads. Essentially what you're doing is either the truck and the lane or the tandem and the lane. So you're going to have to combine these force effects in various fashions, and we're going to talk about that today. In negative bending regions, we have a special investigation that we have to conduct where we basically straddle 2 trucks across the pier to try and generate those additional negative moments that you would get in pier regions. So that leads to 4 load cases. 100% of those 2, or 90% of those 2. And those 2 on that slide are only for negative bending regions. So you'll see when software programs spit out output, when you look at double truck and double tandem data, it's funny how on all the positive values, they're all 0. And that'll become clear here in a second. We then looked at combining those with specific load combinations, and then looked at fatigue limit state and live load deflection. So fatigue limit state, it's basically just a single truck The only difference is that we keep that rear axle at 30 feet. That's just the way the fatigue spec was calibrated. For live load deflection, we use either the truck or 25% of the truck plus the lane. We looked at dynamic effects. You know, when we drive on highway bridges in the United States, and I'm sure some of you think particularly in states like West Virginia, there tend to be a fair amount of potholes on the road, and that tends to make the truck go brrr, you know, add some dynamic effect to it. So we account for this by upping the vehicular component of our load by what are called impact factors. And there used to be this really, I don't want to say convoluted, but a really empirical way to compute impact factors. Now they're pretty simple. And for most cases, we're just going to use an impact factor of 1.33, except for when we do fatigue, we'll use 1.15. And so I provided this, and this is the one slide that I would place a big star on, or at least a little sticky note on for later, because we're going to refer to this pretty exclusively when we actually go into Excel and compute our live load moments and shears. That's going to be pretty important for us later. So that's just something I would sort of keep in the back of your noggin for later. Everybody good? Okay. Now, the live load, that's great and everything, okay? But it leaves two big questions, okay? And the two big questions that this leaves are, if I've got some live load component, I got to answer two questions. Where do I, so let's say this is my truck and this is my bridge. I got two questions to answer. Where do I place the truck along the bridge or longitudinally along the bridge? And then where do I place the truck this way? Okay? Because, you know, in actuality, the structural analysis of a three-dimensional composite steel girder bridge, you know, if you're trying to do it all out, that can be pretty complicated. But we engineers, we don't like complicated. We like simple. Okay? So I'm going to show you some of the simple ways of doing this. And I'm going to take it one step at a time. So the first thing I'm going to do is we're going to talk about how to place the truck this way, longitudinally along the bridge. Okay, so that's sort of part one. We'll talk about the transverse placement later. So let's start off with longitudinal placement, and that means talking about the concept of an influence line. Now, has everybody heard of an influence line before? I've got to believe that you've talked about influence lines in structural analysis. It might have been a while. That's okay. We're going to have a quick review. Okay. So the idea behind this is when you're dealing with permanent loads, structural analysis in its, you know, conceptually is really easy. Here's the model, put the loads on it, get the response. That's all there is to it. When you're dealing with transient loads, however, or live loads, it's a little different because the loads move. Okay? Now, what that's going to mean for us is we're going to start really quickly. We're going to stop thinking about things like moment and shear diagrams, and we're going to start thinking about things like moment and shear envelopes. Because at a given point, we're going to have a potential range of forces that we can see. You know, a possible maximum positive value and a possible maximum negative value. And that'll become clear here in a second, and that primarily results through longitudinal placement. Okay? Now, in order to do that properly, that's where influence lines come into play. So what's an influence line? Okay? Now, if anybody remembers your structural analysis class, probably the first thing that your professor said when they mentioned influence lines is they said they're going to look a whole lot like shear diagrams and moment diagrams. They're not shear diagrams and moment diagrams. They're not the same thing. In many ways, they're kind of the inverse of shear and moment diagrams. So let's talk about how an influence line is generated. So I have some structure, you know, a beam, what have you. I take a single load. In most cases, we take that to be a unit load, like a 1 kip load or 1 kilonewton, depending on whatever unit system you're interested in. And then I take that unit load and I move it across the structure. And as I move it across the structure, I record a response from a point of interest. So a response might be, you know, if I've got a simply supported beam, maybe I'm interested in the reaction over here. So I move that load across the structure, and then as I move it, I say, what's the reaction here? And then I plot that. That plot is the influence line. So let's see what that looks like. Okay, so I want to consider a simply supported beam, and we'll say for the sake of discussion that beam's 80 foot long. It really doesn't matter how long it is, because a lot of this is going to be pretty straightforward. And I've got this one kip load, and I'm moving it across the structure. And I propose whatever goes on down here, this is going to be the influence line for the reaction at A, or AY. Okay? So let's start off with something pretty basic. If I take a single unit load and I put it all the way over here, the reaction here is going to be 1, and there aren't going to be any force over here at all. That's going to be 0, right? So I propose that at the very beginning of this influence line, if I say that x begins here, I say that at x equals 0, that value is 1. Okay? Now let me skip ahead to something a little more basic. Let's say I take that load and I put it smack dab in the middle of the beam. So if I take, one kip and put it right here, half that load's going to go over here, half that load's going to go over here, right? So my influence line value at x equals 40, or at midspan, is going to be 0.5. Make sense? And it's going to be linearly proportional. Make sense? If I put it 20 foot over, that's a quarter of the way over, so this becomes 0.75. That one's going to become 0.25. You kind of get the pattern from here, right? Make sense? All right. So long and short of it is, that is the influence line for the reaction at A. Okay? Now, going back to a concept that might be a little fuzzy, but it's okay. We're here for a little bit of review here. This structure is a structure that is statically determinate. And what that means is that there are as many unknowns as there are equations of equilibrium. It's a statically determinate structure. I've got 2 unknown support reactions here, 1 unknown support reaction there, so 3 unknowns, and I've got sum of forces in the x direction, sum of forces in the y direction, sum of moments. So that's a statically determinate structure. Whenever you're dealing with a structure that's statically determinate, influence lines are always linear, always. Okay? Now, for the bridge, like the one in example 1, that structure is statically, that structure is statically indeterminate. Okay? And it's indeterminate because there's 1 additional unknown. For that bridge in example 1, I've got a pier in the middle, right? And that's where I get that positive bending region and that negative bending region. So because of that, I've got an influence line that's ultimately going to have some curvature to it. So that's just sort of a rule to keep in the back of your head. Influence lines will always be linear for statically determinate structures, nonlinear for ones that are indeterminate. So far, so good? Okay. Now, influence lines help us out quite a bit when we're looking at bridge design because of 2 reasons. Number 1, they graphically tell us where to put the load to generate. It freaked me out. Somebody trying to come in, or? Oh. Cops are after me or something? Oh. I see your faith in me has unwavered in the last week. Influence lines do 2 really important things for us as bridge engineers. Number 1, they graphically tell us where to put the load. Let's keep in mind what this is talking about. This is the influence line for the reaction at A. So what this should have told us before we even started drawing things is that if I want to get the maximum reaction at A possible, I'm going to take the loads and I'm going to lump them as close to A as I can, right? I mean, if I'm designing, the reaction at A and I want to determine the maximum force that goes on A, I'm not going to take the load and put it over here, right? That doesn't make sense, okay? Well, the influence line tells us the same thing. Where are the largest values? Over here. Make sense? Okay, so that's number 1. Number 2, they numerically will help us determine those support reactions directly, okay? In other words, once we determine an influence line for the reaction at A, because we're dealing with a unit load, we can determine the reaction at A for any load. Now, what do I mean by that? Ignore what's going on with the slide, and let's just do a basic example. So let's say I put 20 pounds right smack dab in the middle of this table, 20 pounds. How much goes over here and how much goes over here? 10 pounds. Let's say it's 180 pounds. How much goes here and here? Okay, now how are you doing that? You're just taking it and dividing it by 2, right? I propose what you're doing is you're taking it and you're multiplying it by the value of the influence line at the center, 0.5. Once you've got the influence line for a point, you can determine the reaction due to any load. Okay? Now, like I said, graphically, an influence line tells us where to put those loads to generate maximum force effect. So if I'm looking at, let's say, I don't know, the HL93 design truck, I'm going to take that truck and I'm going to lump it as far over to the left as I can. Okay, so that's number one. Number two, look at my axle spacings. They're 14 feet. Makes sense to keep that at 14 feet. I wouldn't make it 30 because then I'll take these loads and then drag them over here. This is going to cause a lower reaction. If I'm in the design phase, I want to generate the maximum possible force I can so that I know what I'm designing for. Make sense? Okay, so that's point two. Point three, I actually took the truck and turned it around, right? This truck's backwards from what we looked at before. That's okay. Nothing says the trucks have to go this way. Or maybe somebody doesn't know what way they're going down the road. Roads are curvy. People get lost in West Virginia. It's okay. I'm trying to get people laughing. I know it's Tuesday night. All right, makes sense? Makes sense where the truck was placed. Okay, so graphically, the influence line told us where to put the truck. How do I get the actual reaction? Well, I could, let's say some moments at B and go through and do the moment calcs and get the reaction. Or I could just use the influence line directly. Take 32 times whatever the value is here at the influence line. It's a line, so it's rise over run, 1 over 80. You all should be able to get the intermediate values. That's just basic graphing. Sorry. So if I take 32 times 1, 32 times that value, 8 times that value, bam, I've got the reaction. So that's the nice thing about an influence line is it'll automatically do your structural analysis for you. Okay. Once you've got it, you're golden. Okay. Now, what we do. Now, let me back up a little bit. So that is an influence line for what we just saw was an influence line for a reaction. We can very easily do one for shear, for moment. What we do is we have to pick a particular spot of interest and then just do the same thing. Pick a point, draw the influence line. Pick a point, draw the influence line. How do we do that? Move the load, determine the response. Move the load, determine the response. Make sense? Computer programs do a lot of this for us. Okay? On your next homework assignment, I do have a couple influence lines. They're not of any great challenge, but I want you to at least have an idea behind how these computers are doing this. Now, most computer programs written that do influence line analysis use finite elements. So if you're really interested, take finite elements and you'll learn about the programming. It's all about stiffness matrices and assembling and whatnot. See, you know. It's fun stuff, right? All right. Okay, so everybody good? Okay. Now, in the world of bridge engineering, this is how a lot of these computational packages work. Now, what you'll hear referenced a lot from here on throughout the course of this semester are 10th points. And what I mean by 10th points is this. Because of our analysis, or the limits with our analysis tools, specifically using influence lines, we can only draw an influence line at a particular point. I can draw an influence line for the moment right here. I mean, I could try and draw influence lines everywhere, but that would just take a long time, especially when bridges get more and more complex. So what we do as bridge engineers is it's very common to split a span into 10th points. So, for instance, if I've got this 2 90-foot span, continuous span bridge, like example 1, I'm going to take this bridge and divide it into 10th points. So I'll draw an influence line at x equals 9 feet, x equals 18, x equals 27, x equals 36, so on and so forth. And then I'll use those to generate my moment and shear envelopes. Make sense? Okay. Now for an indeterminate structure, keep in mind, again, that's indeterminate. I said, and remember, the influence lines are curved in nature. Okay? So I just wanted to give you kind of an idea of what the pattern would look like. So these would be the influence lines for shear and moment. This is at x equals 9 feet. Now you'll notice as we start progressing, notice how this, if I look here on the left, this is the influence line for shear. I've got this same jump going, and it's going down. Now, without doing too much math, let me ask you this. If I were to take a ruler and measure that, how much is that right there? How much is that jump? 1 kip, right? And that just comes from our sign convention for shear, that once that load drops from one end of that section to another, we have a sudden change in shear of 1 kip. So that's where that value comes from. It's just our sign convention for shear. Make sense? Okay. So here's what's happening as that load, the load moves across the structure, and my point of interest is moving as well. Now, what I really want to focus on is, let's say, this right here. This is a good one. Okay? This idea of moment and shear envelopes couldn't be better explained with this picture. Okay? What I mean by that is this. Let me go back a little bit. Okay? Here is our example for support reactions. And it made sense that if I'm trying to maximize the support reaction at A, I'm just going to throw all that load all the way to the left. Make sense? But now, this is a little trickier, okay? Because right now, I'm drawing the influence line at 36 feet. So here's my bridge, 36 feet from the left support. That's my point of interest, okay? What this influence line is telling me, for instance, if I look here at the moment side, if I put that truck on the left span, I'm going to get positive bending. But if I put it on the right, I'm going to get negative bending. Does that make sense? So in other words, I'll sort of draw that out because I just want to make sure that's clear. Okay. Let me make sure and enable editing. All right. Okay, so what I mean by that, where'd my pen go? There we go. So keep in mind that throughout everything I'm about to draw, my point of interest is right here. Okay? Now what that influence line was telling me is that if I place that truck, I don't know, somewhere right here, that I'm going to get positive bending. Now why am I going to get positive bending? Well, my beam's probably going to deflect something like this. Make sense? It's going to deflect downward. But the thing about that is that this side's going to go up like that. Right? Make sense? So what would happen then, if I took this load and I moved it over here? Over here, this side is going to go down, right? But this side's going to go up, right? So does it stand to reason that if I keep my eye fixed at a point of interest, that there's a maximum possible positive moment and there's a maximum possible negative moment? That that point on the bridge experiences both positive and negative bending. It's all about the range. Make sense? Okay? That's what these influence lines are going to help characterize or help quantify for us. Okay. So let me sort of go continue on with this, and this will sort of make sense. Okay, so these are just what the influence lines look like as you kind of progress. The only thing worth mentioning is that the shear diagram, depending on which way you look at it, right at the support because of the sign convention can suddenly flip over. It doesn't change your magnitudes, just your signs. It's really no big deal, not worth mentioning. So I want to observe this effect, I guess in specificity, going back to that 0.4L. So if I'm looking at, let's say, that particular point, the one I was looking at before, the 0.4L, let's look at that effect right there. So here's my influence line at that particular point of interest. Going back to what I said before, our big interest later on is we're going to be interested in moment and shear envelopes, not moment and shear diagrams. What do I mean by that? Well, if I'm trying to generate maximum possible positive moment at that point, I'd probably place the load somewhere right here. Place that heaviest axle right over the point. Do a little bit of investigation. Say, well, I got larger values over here on the right, so I place that next 32 kips over here. Place that lower axle over there. How do I get the response? 8 times whatever that value is, 32 times whatever that value is, 32 times whatever that value is, right? Make sense? Okay. What about maximum negative moment? Probably something similar, only I've got to place that over here. Make sense? So at a particular point, a maximum possible positive moment, maximum possible negative moment. All right, now that's the truck. What about the lane? Well, the influence line tells me, you know, this is a uniformly distributed load. I place that wherever I need it, okay, to generate maximum effects. So this influence line tells me that for that particular point, I got positive values through here, place it only in those regions, okay? Now, how do I calculate the response? Well, for point loads, it's load times value, load times value, load times value. For distributed loads, it's the load times the area. Make sense? Just the area under the curve. All right. For maximum negative moment, I just place it all the way over on that span. So far, so good? Okay. So ultimately, what a computer program would spit out is something like this. Okay? Now, what I've done is I'm exploiting symmetry right here. I mean, technically, what you would have is something like this. Let me go to my, let's go to this. Okay, technically what you would have is something like this, but if you notice, everything's symmetric because it's the same span length. So, like for instance, if I go to the double truck, see how the numbers are symmetric, like 479, 755, 1196, and then it goes back, you know, 755, 479. Everybody see that? I'm just, you know, for the purposes of the slide, I'm only producing the values from 0 to 90. Okay. But my point is that at a particular point, you know, let's say at x equals 30 feet, there's a maximum possible positive moment, a maximum possible negative moment. And I've got everything reported for the truck, the lane, the tandem. Over here on the very right, I did the fatigue truck. There's not an incredible amount of difference between the truck and the fatigue truck. The truck moments are a little bit larger because I'm able to take those axles and squunch them up to 14 feet. The fatigue truck, I got to keep them at 30 feet. Okay? Now, the double truck and the double tandem, they're zeros everywhere except for right here. Why? Because those are the negative bending regions, right? The bridge is going to experience that frowny face segment right there over the pier. Okay? Make sense? Yes. Well, that's taking the tandem and maximizing it based on the influence line at that 9-foot mark. Now remember, the tandem is two 25 kip axles spaced at 4 feet. So, you know, not squared centered, but probably one on the 9-foot and one on either side. No. Okay, and the reason why is, okay, so here's my influence line. I argue that, or I claim that to get larger moments, take a 25 kip axle, put it directly there. And then the next one, I'm probably going to move it over here instead of that side. I feel like if I go 4 foot over on the right versus 4 foot over on the left, I'm going to get a larger value. Does that make sense? Yes. You're exactly right. Yes. Okay. Now, one thing that I'm so happy I don't have to talk about anymore because they removed it out of the spec, but there used to be a moment shear interaction check, and it made bridge engineers want to pull their hair out. Because what they would have to do is they would have to determine, okay, what's the moment here, and then what's the corresponding shear to that moment. And it's not the same thing as the shear values because, you know, to generate maximum moment at a particular point, you may put the truck, you know, somewhere here, but to generate shear, you may put it somewhere else, and that could be a pain. So, does that make sense? Okay. And this type of stuff that you see in this table, this is the type of stuff that computer programs, they just do on their own. Okay. No bridge engineer, no reasonable bridge engineer would be expected to just do this for every single bridge. I mean, they need to understand influence lines, but I mean, there are programs out there that do this. I don't expect you all to generate this by hand for every bridge. That's a lot of work, okay? What I do expect is that given this longitude, keep in mind, this is all longitudinal data. This is just taking the truck and moving it down the bridge like so, right? This has nothing to do with taking the truck and moving it this way. We haven't even gotten there yet, okay? But this is just taking literally a beam simply supported roller and what have you, and taking that truck, taking that lane, and generating maximum force effects at every 10th point. It's our responsibility to combine it appropriately and distribute it appropriately, and that's where that transverse placement comes into play. That make sense? All right, any other questions? This is good stuff. Okay. All right. What we will ultimately do is, remember that little slide that I told you all to star with all those load combos? We're going to go back to that later on, and we're going to combine these loads, 1.33 times the truck plus the lane, and so on and so forth. And we're going to use that to determine the controlling live load case for a given segment. The only thing after that to determine is how much load goes to each girder. And that's where the transverse placement comes into play. That's where live load distribution is worth discussing. So, any questions about longitudinal placement at all? All right. Let me do something real quick. Let me pull up the transverse placement. So this is what you all have. Let me go ahead and get the sign-in sheet started because I forgot to do that. Now, I will try and reserve myself a little bit when talking about this topic. Live load distribution factors are something that's sort of near and dear to my heart. I did my whole master's thesis on developing live load distribution factors for exterior girders, and I can talk about this topic all day. Okay, but but I will try and reserve myself. So, what's going on here? Okay, well, what we did just now is we talked about the longitudinal placement of a truck. Where do we place that truck along the span to get the maximum force effect at a given point? But what we've got to do is translate that into real life. In other words, what I just did was, the triangle and the circle, the line, the mathematical model that, we use for structural analysis. I have to then translate that into what I would call real life moments and shears. In other words, how much of that analytical model that you just, utilize, how much of those moments and shears are really going to the girders, okay? And that's where live load distribution factors come into play. So here's the idea, okay? So let's say I've got some computer program that spat out some moments and shears for, a bridge, okay? What I would do is I would take those moments and shears and I would multiply them by an appropriate distribution factor, and they're kind of involved, so we'll take our time and discuss it. But I would multiply them by the appropriate distribution factor, and then I would then generate real life moments and shears. So let's say you're looking at, I'll give you an example. Let's say you're looking at interior girders and you're looking at moment. Okay, so you would calculate the worst case distribution factor, and let's say it comes out 0.6, whatever. So what I'm then saying is if I'm looking at that interior girder for cases of moment, I'm saying that whatever my computer program spits out, take those moments and multiply them by 0.6, and I would get real life moments. Now there's some approximation into these distribution factors. There's a lot of research and study that's gone into them, but by and large they do a pretty good job in translating approximate moments into quote unquote real life moments. Okay, so a little bit about distribution factors. Distribution factors used to be pretty simple. You would and arguably the number one, and arguably about it, it's the truth, the number one most important parameter in a bridge that affects live load distribution is the girder spacing. Because if you think about it, the farther apart those beams get, the more load one particular beam is responsible for. Make sense? So in every single girder live load distribution factor, girder spacing is going to be in there somehow. Right? It's going to affect it. Now, it used to be that they were real simple. You'd take girder spacing and divide it by 11, or girder spacing divided by 6 or 5.5, and that was your distribution factor, and that was it. And everything was simple, and everything worked out really well. But the problem is that those distribution factors, those really simple ones, were developed back in the 40s and what have you, and they were developed for a really narrow range of bridges, And don't get me wrong, for that narrow range of bridges, they worked really well. The problem is that engineers, they took these and they plot them everywhere, okay? And they just didn't work everywhere. So a massive research study was done back in the 80s. This was done by Empson and Associates. It's NCHRP Project 1226. NCHRP stands for the National Cooperative Highway Research Program, and it's where a lot of federal highway research is allocated through. And it was done by a company named Empson and Associates out of California, and they did this massive computational study, a lot of finite element modeling, to try and develop more accurate equations. Okay, and this is sort of a before and after in their report, and you can see they're doing a little bit of a better job. This is before before that study, and then using the equations that they developed. The equations that they developed on the face seem a little more complicated, but they utilize parameters that are pretty easy to find. Things like span length, things like things like girder spacing, slab thickness, things like that. Okay, so let's talk about those equations and how to compute them, and then we'll take a break and we'll go through a full example on how to compute them. So one of the first steps to determine livelihood distribution factors is to compute what's called Kg. Kg stands for a longitudinal stiffness parameter. And basically this just is trying to take into account the stiffness of the section associated with the bridge. So Kg is a function of the modular ratio. So this is kind of the way of trying to take steel superstructures versus concrete superstructures out of the equation. Because if you were dealing with a concrete slab and a concrete beam, the modular ratio would be 1 and everything would sort of be washed out. Okay? So your modular ratio, okay, your moment of inertia of just the bare girder itself, just the non-composite steel section, the cross-sectional area of the girder, and then Eg. And Eg is basically the distance from the centroid of just the steel beam by itself to the centroid of the slab. Okay? And this is where some of that empirical stuff comes into play. I mean, a lot of these equations come from, boatloads of three-dimensional finite element modeling, a pile of data, and trying to come up with an equation that matches this data as closely as possible. Now, there's some behavioral observations that go into it, but there's a lot of that happens too. Okay. Now, when you open the code, distribution factors are discretized very carefully. For instance, there are different distribution factors for steel bridges than there might be for concrete bridges, for slab-on-beam bridges than, hollow box bridges or things like that. Okay? There are different distribution factors for girders on the inside versus the two girders on the outside. Okay? There are different distribution factors for single lane loading scenarios or multiple lane loading scenarios. And that might not make a lot of sense, but when you think about it transversely, sometimes having more than one truck doesn't always produce the most extreme effect, because it almost goes back to that reverse curvature idea that we were discussing with the two spans. Now, if you put two trucks, that one truck may want to raise the other girder up. So that can happen as well. And there are also different distribution factors for moment effects and for shear effects. So all right, so I'm not going to go greatly into the spec right now, but I'm at least going to mention some of this stuff. So this comes out of Section 4. You all have this Section 4 in the spec. It's probably a worthwhile idea. But here in a little bit, we're actually going to go through and delve into it. So one of the first things that this section dictates is the different types of cross-sections that are applicable. So we're obviously dealing with cross-section A, a composite steel beam. But you could be dealing with open steel or precast concrete boxes, maybe a cast-in-place concrete multi-cell box, maybe a cast-in-place concrete T-beam bridge. Depending upon what cross-section you're dealing with, go to the table and then, okay, if I'm dealing with cross-section A, cross-section E, whatever, here's my distribution factors. Okay? Make sense? Everybody good on that? So what I'm doing is I'm going through what's listed in the spec. So I want to focus on this lower portion right here. So I've got one design lane loaded or multiple design lanes loaded. Here are the distribution factors for interior girders, and I'm distributing moments in this table. Okay? Now I've got here's my distribution factor, and then there's also a range of applicability. So for instance, the span length. This distribution factor works anywhere from a span length of 20 feet to a span length of 240 feet. And that's by and large a pretty good range for most typical bridge designs. Okay? Now if you've got a two-span bridge where each span is 90 feet, well that still fits because each span's 90. Okay? A girder spacing anywhere from 3.5 feet to 16 feet. That is a heck of a range. A heck of a range. A slab thickness anywhere from 4.5 inches to 12 inches. Pretty good. Okay? Make sense? Any bridge where you have a number of beams greater than 4, which is what we're going to do anyways in America. So no big deal. All right. Now here's exterior girders looking at moment. Anybody see something popping up in that table? Anybody see something? This whole lever rule thing? Everybody see that? My whole master's thesis was trying to replace the lever rule. And I think I did a pretty good job. I had an R squared of 0.99, but one thing you find when you start going through the steps of into the spec is it's really easy to get something in the spec. It's really tough to take something out. Because once engineers get comfortable with something, they don't want to give it up, even if it's better. It's politics, and I'll leave it at that. Okay, so a lot of instances we have to use this lever rule concept. It's this sort of old statics approach. It works, but it usually is way conservative. In other words, it over-predicts the moments that you get, but by quite a bit. So, but I'll leave it at that. All right. Interior girders. For shear, again, similar empirical expressions. Exterior girders for shear, lever rule. Now, if we've got multiple lane loading scenarios, we can also modify our interior girder factors. And don't worry if there's a lot of details and tables and figures flying at you. No big deal. We're going to explore these in great detail. We'll dig into them, make sure that we're clear. All right. So far, so good? All right. This is just a couple notes. The term L, I say L is the span length, but you got to be careful with that. For instance, if you're dealing with a two-span bridge where one span's 90 feet and the other span's 150 feet, what's L? Okay? So if you're in positive bending regions, L is just whatever span you're interested in. But if you're in negative bending regions, let's say around the pier, you take the average of L. Okay? Make sense? It's all about just details and making sure what's going on. Some of these rules seem a little quirky and a little strange. Again, goes back to the empirical approach, taking a massive pile of data, trying to fit an equation that represents that data. So, all right. All right, so let's talk about that lever rule. So the lever rule is sort of a statics-based procedure to get the distribution factor on a given girder. And here's what happens. So I'm going to skip ahead to the next slide. So let's say you've got a slab. Let's say here's your barrier. Now, this is going to be your exterior girder. This is the girder that's next over. So the distance between here and here, that's your girder spacing, right? So here's what I'm going to do. I'm going to assume this is a hinge. I'm going to put my truck on the bridge. Now I'm doing half and half because the truck's going like this in and out of the screen. So half the truck's over here, half the truck's over there. And I'm saying what's that support reaction? Sum of moments equals 0. How much does that reaction have to be in order to hold that truck up? And that's the lever rule, okay? Assuming that end of that bridge acts like a lever. Make sense? Now there are rules as to where you place that truck, and you can go to Article 3.6, which you all have, and I do suggest that you check into that, is that when you're trying to produce extreme effects, you want to take that truck and lump it as far over to the outside as you can, but you can't just lump it over the bridge. And the specs say that that's 2 feet from the barrier or 2 feet from, let's say, the sidewalk or something like that, wherever the beginning of that road begins. Okay, so this is ultimately where you would place the truck. You'd find out where your barrier edge is, 2 foot over, there's one axle or one line of wheels, 6 foot, there's the other line of wheels. Statics. Make sense? Any questions? Now, you geotech folks might actually like this. There is another procedure that we're required to do for beam-on-slab bridges, and it's called special analysis. And I know this equation might look like something out of a nightmare. It's really not that bad, and when we start doing it, it might actually be somewhat familiar. Basically, what we do is this. Special analysis is trying to prevent the cross-section of the bridge from rotating too much. So what we actually idealize, and it's kind of interesting the way this works, we assume that the slab of that bridge is acting as if it were a pile cap, and that each girder was a pile. We place the truck on the bridge, and then this is that approximation method for reactions in pile groups. This is trying to determine how much load would go on each pile, or in other words, how much load would go on each girder. Kind of the same idea with the lever rule, only we're looking at the entire bridge. Now, if this equation looks a little nasty, again, it goes back to just basic mechanics. This first part you can kind of think of as P over A. You know, the number of trucks divided by the number of beams, P over A, plus MC over I. Make sense? This I being sort of the moment of inertia of all the beams, the moment, or this sum of NB, or the sum of the eccentricities, are all the trucks going on the bridge. So this part here is kind of like your moment, and this XEXT is the distance from the center all the way over to the very edge. That's kind of like your C, MC over I. So we'll practice that. Don't worry, it's not that bad. Okay? Okay. Somebody's riding a motorcycle down 3rd Avenue. Okay. Special analysis, we repeat that for the number of design lanes on the bridge. So if we're designing a bridge that has, 12 design lanes, we would do special analysis 12 times. Okay? Now what we're going to see for our example bridge is that the example bridge, if I remember correctly, has 2 design lanes. And the way that you determine the design lanes is you take the clear roadway width and you divide it by 12 feet. And you take the integer portion. Okay, this is something to keep in mind. So if you take the roadway width and divide it by 12 and you get 2.7, that's not 3, that's 2 design lanes. Okay, it's the integer portion. All right, you put as many design lanes as you can fit. Okay, make sense? If you got a really narrow bridge, you're going to put 2 design lanes that are halfway, half and half. Make sense? Okay. All right. Last thing, or one of the last things I think is worth talking about are multi-presence factors. So multi-presence factors are trying to account for coincident loadings on the bridge. So for instance, if you do special analysis and you got 4 trucks on the bridge, what's the probability that those 4 loads are going to be at the same point, side by side at the same time? 4 tractor trailers right side by side at exactly the same moment. Probably pretty low, right? Make sense? We're talking about extreme force effects too, exclusionary vehicles, all right? What's the probability of 4 concrete mixers being side by side? Stuff like that. So multi-presence factors are trying to account for the probability of coincident truck loadings on highway bridges, all right? And the idea is this, that the spec and most of everything we do is built, or at least somewhat built around 2 design lanes. So the multi-presence factor for 2 lanes is 1. Anytime the number of lanes increases, we drop the distribution a little bit just to account for that probability. Now, if we got 1 lane loaded scenarios, we up our distribution factors 20% just to account for that probability. All right, make sense? Now, this note here, we only include multi-presence in 2 things, the lever rule and special analysis. Wait, don't we have to do it in all those other equations? No, they're built in. All these nice empirical equations that you see right here like this, multi-presence is built into it. You don't need to go out of your way to do it, okay? But lever rule and special analysis, you got to go out of your way. Make sense? Okay. What else? Okay, a few final notes. When you're doing the fatigue limit state, remember the fatigue truck is just a single truck. So we only use those single lane loading scenarios. And because we are enforcing it's only a single truck, we don't use multiple presence. So you need to make sure that you're dividing that 1.2 out when you're doing fatigue, okay? Because we're not dealing with multiple trucks on the bridge. We're only counting that single truck going over and over. All right? Now, all I've talked about is moment and shear. What about deflections? I mean, we've got live load deflections. AASHTO just keeps it simple and assumes all the girders deflect equally under live load. So we just take the maximum number of lanes, divide it by all the number of beams, multiply by the appropriate multi-presence factor, and that's it. So pretty simple, actually. Any questions? All right. Here's what I'm going to do. So I think it's probably that time we ought to take a little bit of a break. So I'd say we take a little bit of a break, get back together around, 7:40, something like that, and then we will do a full-blown set of live load distribution factor calcs for that last example, okay? So it'll be somewhat involved. Everybody good? All right. Let me pause this, and we'll take a little bit of a break.